Okay, so let me start with the correction. So last time, at the very end, I mentioned this strong perfect graph theorem. So a graph is perfect if and only if the G, neither G nor G complement contains an induced odd cycle of length at least 5. So last time, I think I wrote on the board, I forgot this last bit, the of length at least 5 bit, which is incredibly important because, for example, a clique or a complete graph is perfect, even though it has lots of cycles of length 3, lots of induced cycles of length 3. But here, so for perfect graphs, this theorem, you're only talking about cycles of length at least 5. It's not incredibly important because we're not going to prove this because it's way beyond the scope of this module, but it's just for your interest. Okay, so just some reminders. So we've got all these symbols: omega of G, the size of the biggest clique; alpha of G, the size of the biggest stable set; chi of G, chromatic number, minimum number of colors, and a proper coloring. And I introduced this notion of an induced subgraph last time. So if you have a graph, G, and a subset of the vertex set, GS, with square brackets, is the subgraph induced by S. So it's the graph with vertex set S, where the edges are just all the edges of G that happen to be in S. It's just kind of zooming in on those vertices of the graph and looking at the structure. Yeah, exactly, yeah. So there's no chords going across the cycle. It's induced, so it's a set of vertices such that if you look at all the edges within them, they form exactly a cycle and nothing. Yeah. Okay, so today what we're going to prove is the weak perfect graph theorem. It was first proved by Lovász in 1972. And it says that G is perfect if and only if the complement of G is perfect. Okay, I think I stated it before that if G is perfect, then the complement is perfect, right? But obviously, that's going to be an if and only if because the complement of the complement is the original graph. So this is equivalent to saying if G is perfect, then the complement is perfect because the other implication is the same. And note that this is clearly this is weaker than the strong perfect graph theorem because, so the strong perfect graph theorem implies this one. This gives an exact structure of what kind of substructures you can contain, whereas this one just says if you're perfect, the complement's perfect. Any questions about the theorem? Do people remember what complement? G complement, you take the same vertex set as G, but you put you kind of switch the edge. The edge set is the complement of the edge set of G. You can think of it that way. Okay, so actually we're going to prove this theorem, but we're going to prove it via another slightly stronger theorem. But we actually prove the following. So G is perfect if and only if, so if I take any subset of the vertex set S, I have the size of S is at most omega of G, alpha of G, omega of the subgraph induced by S times alpha of the subgraph induced by S for all S a subset of the vertex. And note that this applies the weak perfect graph theorem, right? So WPGT is just weak perfect graph theorem because basically if I say, so suppose G is perfect, right? So I'm saying this happens if and only if this condition holds, right? For all subsets. But this happens, so the thing is, this condition is closed under taking complements, right? Because so what I mean is that, so if this holds for every subset of the vertex set of G, then you get that this holds as well, right? And there's a simple reason. It's because, so this is for all, that's a V. Well, because literally, if I fix any set S, I mean, what is this number? Right? It's literally equal to this number. Basically, what I'm saying is if you have a clique in the complement of G, that's exactly the same as a stable set in G. And that's the same, of course, if I zoom in on any kind of induced subgraph. So these things are just simply equal, and also these things here are equal. Right? So if this holds for every subset of S, then you immediately get that this holds for every subset of S, which, if the theorem is true, so this is by the theorem, this theorem, then this would happen if and only if G complement is perfect. So therefore, it suffices to prove this second theorem. Any questions about that? So this proof is really quite nice. I mean, I quite like it. It's quite surprising. So basically what we're going to do, we're going to, well, kind of play around and derive some properties, but then in the end, we're going to boil everything down to some very, very basic linear algebra, which is perhaps a bit surprising. So actually, so it's an if and only if theorem, right? So as is often the case, 1/2 of it's easy. So this direction is, well, somewhat easy. So this direction, I mean, perfect implies the condition on the induced subgraphs. Because if G is perfect, suppose G is perfect, and let S be any subset of the vertex set, well, what do we know? So what's the definition of we're just going to use the definition of a perfect graph, right? So by definition, we know that, well, I'm going to write it this way. So omega of the induced subgraph on S is equal to the chromatic number of this. So this is just by definition of perfect. And remember we proved 2 trivial lower bounds on the chromatic number last time, right? So one was that the chromatic number is bounded below by the clique number, but the other one was that it's bounded below by the number of vertices divided by the stability number, the size of the biggest stable set. And here in G, subgraph induced by S, the number of vertices is the size of S. And so, yeah, so now just multiply both sides by alpha of G of S, right? And you get the inequality that we wanted. So now we prove the other direction. But first, is there any question about this? Okay, suppose that, so now we prove this direction. Suppose that the condition holds. So, right, we want to prove that the graph is perfect. So let's do this by contradiction. So we want to prove G is perfect. So suppose it isn't. And in the end, we want to get a contradiction. So we're assuming it's not perfect. So it's a counterexample to what we're trying to prove. So we can actually assume that G is the smallest graph, so in terms of the number of vertices, which satisfies, maybe I'll give this condition a name, so I'll call this condition star, let's say. Let it be the smallest graph which satisfies star and is not perfect. Because obviously if there's a counterexample somewhere, you can always pick the smallest counter. Okay, so note that every induced subgraph, of G except, including G itself, satisfies star, right? So if I just replace G with one of its induced subgraphs, I get another graph that satisfies star because, well, if it didn't, then G wouldn't satisfy star. You'd have and so because we chose G to be the smallest counterexample, all of the other induced subgraphs of G must be perfect. So every induced subgraph GS, where S is not the whole vertex set, must be perfect by how we chose the smallest counterexample. So all this kind of discussion so far is just to get the following simple kind of fact that if you took a smallest counterexample to this theorem, what you know is that, so if I look at any induced subgraph, which is not the whole graph, then you have the clique number equals chromatic number, by definition of being perfect, and so therefore, the fact that G is not perfect must mean that omega of G itself must be less than the chromatic number. Because if G is not perfect, there must be some induced subgraph which satisfies this strict inequality. But since all the induced subgraph except G itself are perfect, the only possibility is that the graph G itself has a strict inequality here. Is that? So far, it's still not clear how on earth this is going to boil down to linear algebra. Okay, perhaps I'll leave the theorem statement. Okay, so now I'm going to prove a couple of claims. So this is where things start getting a little bit more technical, but hopefully it's not too bad. So I claim that there exists stable sets. Actually, I need some notation first. So define. So just because it makes it easier to write, so define omega to just be omega of G, alpha to be alpha of G, just so I don't have to write the G every time. Okay, so there's stable sets S1, S2, etc., up to S of alpha omega plus 1 in G, such that every vertex of the graph is contained in exactly alpha of them. Yeah, so you've got these stable sets. I'm not even claiming that they're different stable sets, but they're just any stable sets in the graph. And if you look at these stable sets, every particular vertex gets covered exactly alpha times by these stable sets. Maybe I'll call this claim 1. There's going to be another claim. Okay, so first of all, so the stable set S1, I'm going to define it in kind of somewhat arbitrary way. So let S1 be any stable set of cardinality alpha or of size alpha. By the way, the rest of these stable sets aren't necessarily going to be of size alpha, right? But the first one, we can make it be any maximum size stable set. Remember, alpha is the biggest size of a stable set. And then for each, whenever, for the rest of the proof, whenever I just write an omega and I don't specify, or an alpha and I don't specify, it's always going to be the whole graph. At the moment, in the statement of this claim, there kind of is no S. I mean, we're trying to prove that these S's exist, but good question, yeah. Okay, so let S1 be any big stable set and write the elements, just give them some labels. I'm going to call them X1, X2, up to X alpha. And basically, I'm going to go through these elements one by one and look what happens when I delete them from the graph. So for each I from 1 to alpha, the graph, G induced by the vertex minus, so the whole vertex set minus xi as a proper coloring. So as we proved up there, with at most omega of its clique number colors, so which is at most omega, right? Because we know that for any set S which is not the whole vertex set, you have chromatic number equals clique number. So in particular, I can color this graph with omega colors, such that any set of colors or vertices which all get the same color, they don't have any edges contained in it. So let Fi be such a coloring. And so basically the rest of these stable sets are going to come from looking at these colorings and taking the vertices that have the same color. So for, let's say, I between 1 and alpha and J between 1 and omega. So at the moment, I'm just going to call the set Tij. So let this be the set of all vertices V, which get color J under the coloring Fi. So because this is a proper coloring, Tij is a stable set, right? Because it's literally the set of all vertices that get color J, and in a proper coloring, none of those vertices can have an edge between them, so it must be a stable set. And now so the number of such sets that I have is alpha times omega, right? Because there's a Tij for every I and J, I between 1 and alpha, J between 1 and omega. So we now just let S2, 3, etc., to S alpha omega plus 1 be the sets Tij for I between 1 and alpha, J between 1 and omega, and the correspondence is completely arbitrary. So all I care is, the number of things here is alpha times omega, right? And so I can kind of pair them up with these because there's alpha times omega of those. I just pair them up any way I like. Is it clear what I mean by that? So now I need to show that it has the properties we wanted, which is that every vertex is contained in exactly alpha of them. So first of all, if I look at a vertex V, which is not in S1, right, then that vertex got colored by all of the colorings Fi. So then V was colored by every coloring Fi for I between 1 and alpha. So I mean, because yeah, this is not one, because since it's not in S1, it's not one of the vertices we deleted when we defined these colorings, right? And so V is in exactly alpha of the sets Tij, and so therefore it's in it exactly alpha of the sets S2 up to S alpha omega plus 1. And now if V is if you take some element of S1, so remember the elements of S1 are labeled X1 up to X alpha, so each of these Xi's got colored. Well, the only time it didn't get a color is when you looked at the coloring Fi. Remember, Fi colors the vertices. Yeah, Fi is a coloring of the vertices, all the vertices except for Xi. So that was the only time it didn't get a color. So Xi is colored by all coloring F, let's say I prime, except when I prime. It's the only time it didn't get a color. So it is contained in alpha minus 1 of the Tij's, and it is contained in S1 by definition. So therefore it's contained in exactly alpha of the stable set. So every vertex exactly alpha of the sets S1 up to S omega alpha omega plus 1. It's a little bit technical, but this minimal counterexample thing came in very handy, right? Because we can get, every time you delete a vertex, you can find a coloring using colors. Any questions about this proof? Okay, so now one more claim to prove, and then everything's going to come together using a nice linear algebraic trick. Just check. So the second claim is that there exist cliques 1, 2, up to C alpha omega plus 1, such that, if I look at the intersection of Ci and Sj, so Sj, so the S's are the stable sets from the previous claim. So this is 0 if I is equal to j, and it's equal to 1 otherwise. So this is, of course, for I and j between 1 and alpha omega plus 1. Yeah, so the way you do this is basically you just take, first we're going to show that, the first condition we need is that for every each of these stable sets Si, we need a clique Ci which is disjoint from it, right? So for, let's say, you need that Ci intersect Si. Well, we need a clique Ci such that these things are disjoint. And basically, this is the main thing. So if you can find these cliques, right, then we're going to show that they also completely satisfy this property. But the key thing is to find this clique. So I need one more thing. So I want to also say that these cliques have cardinality omega, so such that this happens, and Ci has size omega for all I. So these are cliques of the biggest possible size. If Ci, as in this first sentence, doesn't exist, then I know that the clique number of the graph induced by, the subgraph induced by the whole vertex set except for Si, so if you delete Si, then this clique number would be less than omega, which is the clique number of G, right? Because if it was equal to the clique number of G, I just find that clique, and that's a clique which is disjoint from Si. But remember that this implies that the chromatic number of this graph, which we already know is equal to the clique number, we proved that earlier, would be less than omega. So we can find a coloring, so there exists a coloring F from the vertex set of this graph to 1 up to, say, omega minus 1, this graph. But this is actually a contradiction, because then we could color the original graph using omega colors. So now map each vertex Si to color omega, right? And this gives a proper omega coloring of G, but that's a contradiction, right? Because we proved earlier that G has chromatic numbers strictly larger than omega. So therefore, these cliques Ci, they all exist. Yeah, so I understand all of this sort of maybe seems a bit technical. I'm trying to go slowly through it, but I think every step of it individually, we thought about it, every step is sort of easy, but there's just kind of a lot of steps that accumulate. Okay, so by the way, we've constructed this thing, so we know that for all I. Now we need to prove the other part, that so we need to prove that Ci intersect as j equals 1 for j not equal to I. right? That's the part we haven't proved yet. Okay, so one thing is clear. So clearly, if I look at this intersection, it has to be at most 1. And that's just because one of the sets is a clique and the other one's a stable set. So if you think about it, how on earth could they share 2 vertices? Because those 2 vertices, since they're in a clique, they must be adjacent. And since they're in a stable set, they must be non-adjacent. So there'd be no kind of way to do this. So this is certainly a most 1 because Sj is stable and Ci is a clique. And now we have to prove that it's exactly equal to 1. So this is kind of an interesting trick. So what we get is that if I sum overall ij between, okay, maybe write this as like sum I from 1 to alpha omega plus 1, sum overall j 1 to alpha omega plus 1. If I take this whole sum, what I know is that this is going to be at most alpha times omega. No, sorry, I don't want to take this whole sum. I want to just fix, sorry, now this is correct. Because I know that when j is equal to I, you get 0. All the other times you get most 1. So this is at most this. But every vertex in Ci is in alpha of the sets Sj. And so if you think about it, it'll be counted in this intersection exactly alpha times. And the size of Ci is omega. So this has to be at least alpha omega. So this inequality is proved by that sentence. Omega elements in Ci, all of them have to be counted at least alpha times in this sum because they show up in alpha of these sets. So this sum is at least alpha omega. So therefore it must be equal to alpha omega. So therefore this sum is equal to alpha omega. But that can only happen if all of these things were equal to 1 except for when I equals j. So if you think about it, the fact that everything in this thing must have been tight. So it must have been 1 every single time. Could have been. So this is a kind of subtle argument, but if you wanted to do it more carefully, right, you could think of, what if one of them was 0, and then you'd get this upper bound with an alpha omega minus 1, but the lower bound that would contradict the lower bound. Okay, so that proves claim 2, and now comes the grand finale. So now we're pretty much done with the proof of the theorem. So if we let A and B be matrices, so the number of rows of each of them is going to be alpha omega plus 1, and n columns, where n is the size of the vertex set of G. And by the way, so label the vertices. So at this point, it's going to be convenient to label our vertices of the graph. So the vertices are called V1 up to Vn. So these are m by n matrices. And now let me define what the matrices are. So the entries of A are, so Aij equals 1 if Vj is in Si, and it's 0 otherwise. Right? So this makes sense, right? Because the I tells you which row, j is which column. There's 1 row for every Si. There's 1 column for every vertex. Cj is the vertex. Bij is 1 if Vj is in Ci and 0 otherwise. Okay, so these are kind of the columns, rows of this thing are kind of the indicator functions of the cliques or the stable sets. So now, what if I look at this matrix, A times B transpose? Well, so the kind of ij entry of this, so if I look at the ij entry of this, it's going to be like taking the ith row of A with the ith column of B transpose, which is the jth column of B transpose, which is the jth row B, and taking their dot product, right? So the ij entry is the dot product of the ith row of A with the jth row of B. And if you think about it, this dot product exactly counts this intersection, Ci intersect Sj. Or sorry, in this case it'll be Si intersect Cj. So this is going to be the matrix where the ij entry is Si intersect Cj. Cardinality is the ij entry, which by the claim is just the matrix which has zeros on the diagonal and has ones everywhere else. So now all we care about is that the rank of, so what's the rank of this matrix? So this is going to be So the dimensions of this matrix is alpha omega plus 1 by alpha omega plus 1. You can just, if you think about, remember how matrix multiplication works. And so the rank of AB transpose, you can see because the rows are linearly independent, this is equal to alpha omega plus 1. But it's a standard theorem that this is at most the minimum of the rank of A, or the rank of B transpose, which is at most n, because you can't have rank higher than the number of columns you have. But this tells you that n is at most, or is at least, alpha omega plus 1. This is a contradiction, because going back to the very beginning, we assumed that this was the case. This was our original assumption. Okay, so we're over time, so that's see you tomorrow.